Hi, my name is Patrick Klose and I'm going to give you a short glimpse into our work on simulated autonomous driving.
Hi, I'm Rudolf Mester. I'm Patrick's advisor here in the Visual Sensorics and Information Processing Group at Frankfurt University. What we are going to show in the following builds on the idea of letting a simulated agent drive a simulated car in a simulated realistic road network using reinforcement learning.
Our work is also described in a recent paper available on arXiv entitled Simulated Autonomous Driving in a Realistic Driving Environment Using Deep Reinforcement Learning and a Deterministic Finite State Machine. We would like to start the demonstration of our developed system by explaining the driving environment. In our work, the environment is represented by a simulated city with a real road network created from OpenStreetMaps. Therefore, all the roads have a geometrical structure like in the real world. As you can see, the simulation is not a photorealistic one, but all the elements, like for example the road surface, the sidewalks, and the vegetation are semantically colored like an intelligent perception system would also compute it. Furthermore, all the buildings have true footprints but are hallucinated with respect to their 3D shape. The car is based on a physically well-behaving model of a BMW M3, and it only provides the agent with its longitudinal and angular velocity as well as with sensor readings from a simplified LiDAR system. Our system, which we call Reinforcement Learning Based Driving System, is mainly based on the idea of combining the Deep Q network algorithm and a deterministic finite state machine to provide the agent in each driving situation only with reasonable actions from which it can then freely choose. This fosters the exploration of the agent and accelerates the training. Now, after this short introduction into the driving environment and our system, we show the training phase of the agent. It can be clearly seen that initially the agent cannot keep the car on the road, causing collisions every few seconds. This is not only due to the missing knowledge of the agent about how to drive a car, but also due to the exploration of the agent. In our system, the agent starts by fully exploring its possibilities in the training phase to learn which actions lead to high and which ones to negative reward. All the upcoming clips will show the agent after the training phase has finished. As you will see, in this state, the agent can successfully steer the car through different complex driving situations. In the first driving situation, the agent successfully controls the car along a straight road by driving it on the right and keeping its velocity smoothly around the target speed of 8 meters per second. The next situation shows the agent in the situation of handling a wide curve, and again, the agent does a great job at it. The next two clips show the agent in the complex situation of driving the car through a narrow curve. After having tried to drive such curves many times in the training phase, the agent has learned to reduce the velocity only when needed, because too anxious driving would be penalized. The next four clips show the agent when dealing with different intersections. This situation is similar to the previous one, but this time the agent also has to decide which direction to take and then has to stay with this decision until the car was driven along this part of the road. In our system, this strategy of decide what to do and then stay with this decision is implemented using a deterministic finite state machine. As you can see, also in these complex situations, the agent does the job very well. The last clip shows the agent in the situation of facing a combination of all the previous situations. it can be seen that our approach created an agent capable of driving a physically well-behaving car in a realistic road network, and that all the necessary driving modalities could be automatically learned by using reinforcement learning.